Hello students. So this is a lecture series on discrete Fourier transform, a very important topic in signals and systems for GATE, for electronics students. Whole lecture series on signals and system will be uploaded later, but discrete Fourier transform, fast Fourier transform and filter design will be uploaded in few days. Why this is being done by the team of Edamigo is that because DFT, FFT and filter design are the topics which are left by many of the available material in the market, and these are the topics which are very important for upcoming gate exams and other important competitive exams for electronics students wherever signals and system is in syllabus. So in this lecture series, we will start with discrete Fourier transform. We will be covering fast Fourier transform and filter design in the upcoming lectures. This is an initiative started by Edamigo team. So let's start with discrete Fourier transform. So first of all, I should make it clear that I will assume that you have completed or you know discrete time Fourier transform, a little bit discrete time Fourier transform. Uh, so let's start. So first of all, I will give you a brief introduction of discrete time Fourier transform. There are one or two properties that will be used in discrete Fourier transform, and then we will just start discrete Fourier transform. So we know that discrete time Fourier transform where a discrete non-periodic signal, xn is a discrete non-periodic signal, is converted into x e to power j sigma, where sigma is discrete frequency. Okay, so wherever I use this term, it means it's a discrete frequency, and omega is continuous frequency, right? Okay, so and we know the formula also, x e to power j sigma is equal to summation n equals to minus infinity to infinity xn e to power minus j sigma n. Okay, so this is the formula of DTFT. One more thing, that this function, we also know that this function is continuous function because sigma is a continuous variable, right? Also sigma is periodic, or I can say that the discrete frequency axis is periodic with period 2 pi. Discrete frequency axis is periodic with period 2 pi. Okay, so I can say that this function is a continuous function and it is periodic function with period 2 pi. Okay, so this is a very basic of DTFT. One more property that I will use is if xn is a non-periodic signal, discrete time signal with DTFT x e to power j sigma, yn is also a discrete time non-periodic signal with y e to power j sigma as a DTFT, then xn m- convolved yn. Okay, so convolution in time domain corresponds to, or I can say that a signal which is equal to xn convolve yn will have dtft equal to x e to power j sigma, that is dtft of xn multiplied by dtft of yn. Okay, so this is a convolution in time property that you have already read. I am assuming that dtft is already completed by you. Okay, or even if you have not completed these two properties, you all know, because these are very simple properties. Okay, so let's start now with DFT, the topic of the lecture series. Discrete Fourier transform, DFT. Okay, now the first question is, why do we need DFT? We already have DTFT. So the first question is, why do we need DFT? Okay, now the solution to this is, since, because these type of questions are asked in interviews. Okay, so these are very important questions that you should know the answer. So since DTFT has output x e to power j sigma. Okay, so we know that if xn is given to the DTFT function, then the output is x e to power j sigma, which is continuous plus periodic. Now since this is continuous and periodic function, so it has infinite information. From minus infinity to infinity, it has infinite amount of information, which is very very difficult to store in any digital in any storage. So the so what's the problem? The problem is this function is continuous and periodic from minus infinity to infinity. So if we want to store the information, it will take infinite space. So for ease of computation, we do the sampling of x e to power j sigma. Okay, we do the sampling of x e to power j sigma. If we take n samples in one period of x e to power j sigma, then it is called n point DFT of DTFT. Okay, so there's one more definition. I will be coming to that uh, in a bit. So xn was a non-periodic discrete. It has DTFT x e to power j sigma. Now I am doing the sampling of this. So I know that it is periodic with period 2 pi, and in one period I am taking n samples, capital N samples. So I can say that I have generated a new function, that is xk, that is equals to x e to power j sigma, where sigma is equals to 2 pi by n into k, where k goes from 0 to n minus 1, right? Is it okay? Because you have to take n samples in one period. Okay, so this is how you can write the expression. So this is n point. So since we are taking n samples in one period of DTFT, so it is n point DFT of xn. Okay, I can write it n point DFT of DTFT also, because I am taking n point samples of DTFT, and since the DTFT was of xn, so we say that n point DFT of xn. So I will write it here again. So if we take n samples of DTFT of xn in one period, then it is called n point DFT of xn. So is it clear? So this is the important definition that you should learn. So one more thing, you don't have to write all these, because I will be sharing the PDF of the notes that I'm preparing while writing the while giving you the video. Okay, so you don't have to write everything. Just I will be sharing the PDFs. You just download it, and that will be useful to you. It will work as your notes also. Okay, so this is the definition of endpoint DFT. Now a very important point. Now we know that how do we do sampling of any signal? By multiplying it with the impulse train. Okay, so sampling is done by multiplying the signal with the impulse train. So taking n samples in one period of DTFT means multiplying x e to power j sigma, that is DTFT, with the impulse train. Okay, and impulse train should be such that in one period of DTFT, that is from 0 to 2 pi, there should be capital N number of impulses. So I can say that the impulse train should be of the format delta sigma minus 2 pi by capital N k, where k goes from minus infinity to infinity. Okay, so I am sampling the DTFT from minus infinity to infinity, but generally only one period is important. Then also I can see that in one period, that is from 0 to 2 pi, there will be capital N number of impulses. Okay, so or I can say that, so sampling of x e to power j sigma is done by multiplying x e to power j sigma with the impulse train, given in equation number 1. Okay, so now very important derivation. You do not have to write this whole derivation, just look through the video and understand how I am deriving it. The end result is very important. Okay, so only the end result is important. So we started with xn, which was non-periodic, this is very important derivation, non-periodic discrete okay. So this was periodic with period 2 pi and it was continuous also. So now let us assume that let p e to power j sigma is the impulse train that is used for sampling the DTFT of Xn. So the impulse train has n number of impulses in one period. So I will take, so we know that since DTFT is always periodic with period 2 pi, so the definition of this, as we have seen already, is this. So this is defining the DTFT from minus infinity to infinity on the omega axis. But this can be written like this also, because this can be written, so this is actually defining DTFT on whole sigma axis, okay. But we can define DTFT for only a single period also, then also the definition is complete, because we know that DTFT is periodic with period 2 pi. So this is actually defining DTFT, okay, but DTFT in one period only, okay. And we know that since it's periodic with period 2 pi, so it will repeat itself again. So both the definitions are correct. And we know that DTFT can be defined for whole axis, or it can be defined for a single period also, then also it's correct. So let us take this definition, and p e to power j sigma is equal to this. Now, since we know that one has DTFT equals to delta sigma, sorry, 2 pi delta sigma, 2 pi delta sigma, okay. 1 upon 2 pi will have DTFT delta sigma, okay. Here also I am defining only for one period itself DTFT, okay. One has DTFT 2 pi delta sigma, it is only from one period, that is from minus pi to 2 pi, minus pi to pi, okay. So again, so here also I am defining for one period only, okay. Now delta sigma minus 2 pi k by n, we know frequency shifting property, that is the effect goes with the opposite sign, 1 upon 2 pi e to power plus j 2 pi k by n, right. So if Pn is a time domain signal that has DTFT p e to power j sigma, then using these three relationships I can easily convert p e to power j sigma into Pn. So I can say that Pn, here only I can convert it, do summation here on the right side from k equal to 0 to n minus 1. So summation will be done at the left side also, 0 to n minus 1, okay. So Pn is equal to okay 1 upon 2 pi okay. So this is the time domain signal which has DTFT equals to p e to power j sigma, right. And what is p e to power j sigma? That's the impulse train, okay, we know that. Now if we look at the expression of Pn, then we can resemble it with DTFS. Okay, recall DTFS formula. The DTFS formula says that if Yn is periodic with period capital N, then Yn can be represented as okay, k equal to 0 to n minus 1. Now I can compare these two. Okay, now I can say that by comparison that Pn is periodic signal with period capital N, and DTFS coefficients of Pn is 1 upon 2 pi from 0 to n minus 1. Okay. Now another very important point. We know that DTFS coefficients are constant values only when the signal is an impulse train. Okay. So Pn is an impulse train with period capital N. So Pn has expression something like this: A delta n minus capital N m, where m goes from minus infinity to infinity. Okay, so it's an impulse train periodic with period capital N having impulses with amplitude capital A. Now we have to find the value of capital A. How do we get that? We know that DTFS coefficients can be calculated as Ck is equal to 1 upon time period summation n equals to 0 to n minus 1 Pn e to power minus j 2 pi by n nk. Okay, so here the summation is done only for one period, and in one period Pn is equal to delta n only, because in one period only one single delta is present. Okay, so for example, if you draw Pn, then it is n axis, the signal is Pn, so it is present at 0, then it will be present at capital N, then it will be present at 2n, and so on. So in one period, that is from 0 to n minus 1, only one delta is present, that is of height a. So in this summation, it is Ck. In one period, Pn can be written as a delta n (0 to n minus 1). So this delta n is valid only at n equal to 0. So in this whole summation, we will put n equals to 0. So Ck is equal to capital A divided by n. Now since the Fourier series coefficients of Pn was 1 upon 2 pi, so I can say that capital A is equal to n upon 2 pi. And finally, I can say that Pn is a signal that is n upon 2 pi delta n minus capital N m. So m going from minus infinity to infinity. Okay, so this is your Pn signal. If you do not understand any of the step in this whole derivation, then also it's not a big deal, because final conclusion is very important. This whole derivation is just to make you understand if in any case you are going for any IIT interview, then these kind of derivations are very helpful because they used to ask such kind of derivations. Because I have gone through all the IIT's interviews and I know many students and they have faced difficulties in derivation. So even if you give the interviewer half of this derivation, then also he will be satisfied and that will be more than enough. Okay, so now we started with xn, which has dtft x e to power j sigma. Now we planned to sample it. So how do we sample it? We sample it by multiplying the impulse train, and the impulse train function is p e to power j sigma. Multiplication in frequency domain is actually convolution in time domain. Okay, so this will give me, so this first, this what is the equation number? We've used somewhere, no? Equation number 1 was there. Okay, so 1 is only there. So this is equation number 2, this is equation number 3. Okay, so equation number 2 is simple dtft. In equation number 3 we have sampled the dtft, and this is called now n point dft. And if you look at this time domain signal, then what is it? It is xn convolve n by 2 pi summation delta n minus nm. Okay, now if we neglect this constant term n upon 2 pi just for sake of simplicity, so I can say that it is actually xn convolve, where n goes from minus infinity to infinity. Okay, so what is this? Okay, so first of all, try to observe what is this. This is simply, if you look at the expression, then this is simply a new signal. For example, x cap n, for example, let us say that this is a new signal, that is x cap n, where x cap n is created by repeating xn after integer multiple of n. Okay, so if xn was non-periodic, with length L. What is length? Length is actually the number of non-zero values present in xn is length. So for example, if I take just an example, so let us say take xn is equals to a signal which was 1, 1, 0.5, 2, 1. So it's like this: 0, 1, 2, 3, 4, and rest is 0. So its length is 5. Okay, so its length is 5 because there are 5 non-zero terms in it. Now x cap n. What is x cap n? X cap n is actually formed by repeating xn after every capital N integer multiple of capital N intervals. Now capital N has to be greater than 5, otherwise the shifted version and xn the shifted version of xn and xn will overlap each other and the signal will be distorted. So remember that n should always be greater than equal to L, that is the length of the signal. Okay, so let us take that n is equal to 7 for example. So x cap n is formed by repeating xn after 7, 14, 21, minus 7 and so on. So x cap n is equal to xn xn plus xn minus 7, xn minus 14 and so on, and similarly there is plus xn plus 7, xn plus 14 and so on. Okay, so we will be getting 1 1 0.5 2 1, so 0 1 2 3 4, and it will repeat itself from 5 6 again from 7, so it is 1 1 0.5 2 1 7 8 9 10 11, again it will start from 14 and so on. 5 and 6 will be 0, similarly 12 and 13 will be 0 and so on. So I can say that, okay, so is it clear? So I can say that x cap n is discrete but periodic with period capital N. Okay, so a very important conclusion is that, so I'm concluding from here. Okay, I'm just continuing from here, so I will just copy this equation. So equation from equation number 3. So this is your endpoint DFT where we have taken n samples. It can be written as x e to power j sigma, where sigma is equals to 2 pi k by capital N. I'm defining it only for one period, okay, where k goes from 0 to n minus 1. Okay, right? So like this we can write the sampling. So I can say that x. Okay, so it is equal to xk, that is equal to x e to power j sigma, where sigma equals to 2 pi k by n. So x0 is equals to x e to power j sigma, where sigma equals to 0. Similarly x1 will be x e to power j sigma, sigma equals to 2 pi 1 divided by n, where k equals to 1, no? So similarly x2 will be x e to power j sigma, k equal to 2, 2 pi by n into 2 and so on. Okay, so this is the DFT that is n samples of DTFT. It will correspond to the time domain signal, that is x cap n, that is equal to xn minus nm minus infinity to infinity. Okay, now, okay, so now the conclusion. Now I can write that x cap n corresponds to xk. Okay, so where this is DFT, endpoint DFT, endpoint DFT. Okay, so we started with xn, which gives DTFT x e to power j sigma. We sampled x e to power j sigma by taking n samples in one period. We get endpoint DFT, that is x capital Xk, but capital Xk does not correspond to xn. Rather, capital Xk corresponds to x cap n, which is periodic discrete. Periodic with period capital N and discrete. Now if you look at xk, now since it's a sampled version of DTFT, which has which was periodic with period 2 pi, and we have defined xk is equals to x e to power j sigma, sigma equals to 2 pi k by n. Okay, now if you put k equal to 0 here, so you will get x0 is equals to x e to power j0, x1 is equals to x e to power j 2 pi by n, x2 equals to e to power j, sorry, x e to power j 4 pi by n. Now if you want to find now if you want to find x capital N, so you will put k equal to capital N here. It will be x e to power j 2 pi, and x e to power e to power j 2 pi is equal to e to power j 0. So I can say that these two terms are equal. Similarly, x of n plus 1 is equals to x e to power j. I have to shift it more. Okay, e to power j 2 pi by capital N, n plus 1, that will be equal to x e to power j 2 pi multiplied by x e to power e to power j 2 pi by capital N. Now e to power j 2 pi is equal to 1, so I can say that it is equal to 1 multiplied by e to power j 2 pi by capital N. So these two will be equal. Similarly, x n plus 2 will be equal to e to power j 4 pi by n. So these two will be equal. So I can say that capital Xk is discrete and periodic with period n. Also, the time domain signal which this xk corresponds is x cap n, where x cap n is also discrete and periodic with period capital N. So this is the whole conclusion that is very, very important. I will write you in a very simplified manner that all we have done. Okay, so the conclusion of this whole lecture. Okay, so we started with, I will be writing here in a very small format so that the conclusion is there. So we started with xn, which has DTFT x e to power j sigma. We sampled it taking capital N number of samples in one period. So it is xk, that is equals to x e to power j sigma, where sigma equals to 2 pi k by n. But now the time domain signal is not xn, rather it is x cap n, which is equal to x n minus nm, n going from minus infinity to infinity. Okay, so whenever we take DFT of any signal, endpoint DFT, then the time domain signal is also periodic with period n, and it is discrete. This is also periodic with period n, and it is discrete. So this is the whole conclusion that is very, very important. Then that is, in endpoint DFT, both sides are periodic with period capital N, and both sides are discrete. So we'll be continuing DFT in the next lecture. Thank you.